controversial. And to understand chemistry is to understand the process by which components came to be accepted knowledge. Democritus, a Greek philosopher, was called atomos. Though this marks the first time matter was viewed in this way, it was more when Dalton came along and provided the first empirical evidence that atoms in certain observations. For example, when a sample of water was split into hydrogen and oxygen, the result was always 1/9 hydrogen and 8/9 oxygen by mass. With atomic that all have the same exact number of hydrogen and oxygen atoms. Then, no oxygen by number of atoms, and therefore also in the way certain elements combined to form different compounds. If carbon reacts completely with either a certain or exactly 2 oxygen atoms. This was the first solid evidence that atoms exist. Showed that the atom must consist of smaller particles when discovered the electron. In his cathode ray experiment, particles have within them positively charged and negatively charged particles, but he did not know how they were distributed, so fired positively charged alpha particles, which are through to the detector on the other side. But scattered wildly and with high energy in random can hit you. This suggested that the positive charges in the center of the atom, which was given the name nucleus, (5% empty space. That's why alpha particles typically pass right through to strike a nucleus. The huge repulsion between the positive charges makes them fly violently in a random direction. Which we'll have to wait for a little later in your understanding. And have proven a thing or two about their structure.
Righty, we've done enough history of the atom. We're going to move on to our notes. We were right about here. Atom, the smallest particle, and Dre vignette. Those questions are about 4 points each, like we said. All right. So right here on atom, smallest particle of an element that retains the chemical properties. All right, sorry. All atoms consist of 2 regions, the nucleus and the surrounding the nucleus is the electron cloud. All right, so the parts of the atom, first one we're going to talk about is protons. Those are positively charged and they're located in the nucleus. The number of protons does not change. It does not vary unless you're talking about some kind of nuclear reaction. So the number of protons, I'm going to write it like this, which is the atomic number, identifies or IDs the element. So in other words, if I say element number 6, that's in reference to its atomic number, and that would be carbon. So our symbol is going to be a P with a positive sign. It has a charge of +1 and a mass of 1 AMU, which just stands for atomic mass unit, which was a special unit that was derived just to use on atoms. Next one is neutrons. They're high energy, they're neutrally charged, and they're also located in the nucleus. The number of neutrons can vary with an element. It'll be differences in isotopes. We'll talk about that in a little bit. Neutrons stabilize the nucleus by nuclear forces. And nuclear forces are short range proton-neutron or proton-proton, neutron-neutron forces that keep the nucleus together. So you don't have something that's positive and negatively charged to hold the nucleus together. So these forces would be able to do that. Jesus, sit up, sir. Symbol would be N with a little superscript 0. That's called a naught, N-A-U-G-H-T. Charge is 0 because we said it is neutral. And its mass is 1 AMU. So it's about the same as a proton as far as mass goes. All right, and then our last particle is an electron. All right, so let's see. Electrons are negatively charged, and they're located in the electron cloud. The number of electrons can vary from an element, and if that's the case, then instead of them being neutral, now they'll be ions. Electrons are responsible for the chemical reactivity of an element because they form bonds or shared or transferred in that process. The symbol is E with a negative sign. It has a -1 charge, and its mass is 1,836 AMU. So all of them are small, but protons are about equal to neutrons, and both of those are a lot or larger than an electron. The nucleus contains most of the mass of the atom because that's where the 2 heavier particles are, and the electron cloud contains most of the volume because electrons can spread out. The electrons are held around the nucleus by electrostatic. Anybody know what electrostatic attractions are? Electrostatic is when you have something that is positive and something that is negative, and so opposites attract. So since your nucleus is positive, your electrons are negative, then that's what keeps the electrons kind of around the nucleus. Electrostatic forces. And really, as we've been going over how the atom was discovered and all those different things and what you saw in the video, that's really more physics side, really than chemistry. All those different experiments had to do with physics. So now that we've talked about them and identified them, we're going to see how they work in an atom. So isotopes are atoms with the same number of protons. So that means the atomic number is the same, but different numbers of neutrons, and that'll make their mass number different. If you remember from middle school, mass number is equal to the protons plus the neutrons, adding those two together. So if my neutron varies in an isotope, then that's going to make my mass number different because a proton number does not change. Usually isotopes are referred to by their name or symbol with the mass number after it. Every element on the periodic table has at least 2 isotopes, and some have many, many more. So isotopes have the same chemical properties, but different masses. We're going to look at some of the notation. The notation that has the most information is called nuclear notation. I'm going to use sodium, and the symbol for sodium is Na. So if I have Na, that would tell me I'm talking about sodium, and then in front I would have an 11. And then at the top, I would have a 23. The 11, the smaller number, is the atomic number. And then the larger number would be the mass number. Called nuclear notation because it gives you all the information about what's in the nucleus. Sometimes you may just see a symbol, so like sodium -23, or maybe the word sodium -23. If there's just one number behind it, that's always the atomic, not the atomic mass, the mass number. Because the atomic number you can always find as long as you have a periodic table. So if you see something that just has one number, it would always be the mass number. If we look at all this information right here, sodium, once again, your symbol, 11, that's your atomic number, which for some reason is represented by a Z. Your mass number, your larger number, is represented by an A. On your periodic table, on this one up here, and also your yellow ones, the number that is underneath the symbol is the average atomic mass. It is not the mass number. Sometimes you have to use it for a mass number, but it's actually the average mass of all isotopes, and we'll learn how to do that tomorrow. All right, a nuclide is just a general term for any isotope of any element. So like hydrogen has 3 isotopes, so you can say it has 3 nuclides. All right, atomic number is the number of protons in the nucleus. And once again, like I said, atomic number identifies the element. That will not change. Because atoms are neutral, they contain the same number of electrons and protons. So therefore, my atomic number is going to tell me how many electrons I have in a neutral atom. It actually, by definition, is the number of protons, but if it's neutral, it can also tell you that. Mass number is the total number of protons and neutrons in the atom's nucleus. So if I wanted to find the number of neutrons, I would take my mass number and subtract my atomic number, and that difference would be my number of neutrons. Hydrogen has 3 isotopes, and they actually each have their own name. Hydrogen is element number 1 on the periodic table. It has atomic number 1. So that means all of the isotopes have 1 proton, because that's not what changes in the isotope. They're all neutral, so that means they also have one electron, because I need my positives and negatives to cancel out. And how they're different is by the number of neutrons that they have. The first one, protium, only doesn't have any, I'm sorry. Deuterium has 1, and tritium has 2. So if I took and I wrote the notation, I would do hydrogen, and for this one, it would be 1. It has a mass number of 1 because it only has 1 proton. Hydrogen -2, and my last one would be hydrogen -3. All right. This one would be hydrogen -3. Those would be how those would be written. All right. If you like a little mnemonic to help you memorize things, 8-man is a little mnemonic that you might find handy to tell the difference between atomic number and mass number. So let's try some examples of those at the bottom there. All right. So uranium, its symbol is U. Carbon is C, potassium is K, and interesting. Seeing if we were all awake, I guess. Get mine. I know it. It's a bad habit of mine. Believe me, I hear about it often. You can see it doesn't really actually help me, does it? Just see how many tabs I have open on my phone. Like I don't realize it until I just start trying to get rid of them. I also have a whole lot of things on my desktop, which is another thing that bothers some of my friends. Let's try that again. All right, uranium. We said that one was U, carbon C, K, and N. All right. So we're going to look at how many protons, how many electrons, and how many neutrons. So uranium is element number 92. If you look for it, it's in one of the pulled out sections below the periodic table. Yeah. Uranium is radioactive. That's what those elements in that are. So it has an atomic number of 92. So that means it has 92 protons. And because it's neutral, it also has 92 electrons. And then to get my neutrons, I would take my mass number, 235, subtract my atomic number, 92. And that difference, 143, that would be how many neutrons I had. So I put out the little calculator. Some people's minds are too tired to do that. All right, so y'all try the other 3. I gave you their symbols, and they're not as far down. They're like in periods, I don't know, 2, 3, or 4. Remember, your periods go across. So see if you can figure out how many of each particle you have on those. Don't forget, you also have your yellow periodic table. Potassium's number 19. All right, for carbon, how many protons did we have? Which means we also had 6 electrons and eight, not 18. Give a lot of neutrons. All right, potassium. 19, 19, and 20. And sodium, 11, 11, and 12. Now, if for some reason you don't have the atomic number, or I'm sorry, if you don't have the mass number, then you're going to have to round the atomic mass, which is what you see on the periodic table, to the closest whole number, and then you would use that. So for like example, sodium, which is element number 11, if you weren't given the mass number, then you would round that 22.989 to 23 and use it. But remember, when you're talking about these particles, you can't have half of a neutron, so it has to be a whole number. All right, so these are all neutral atoms where your protons are equal to your electrons, and we're going to talk about ions next. So if you go maybe a page over or so, I'd put it in a blank sheet of paper for you. We can talk about ions, which we use a lot. All right, so ions, they are atoms that have lost or gained electrons to become more stable. Noble gases, they're stable because they have an octet or 8 valence electrons. So when atoms form bonds, that's the reason they form bonds. It's leading to a more stable valence electron configuration. So metals, remember, metals are most of the periodic table. So metals will lose electrons. So remember, they're losing something negative. So when they do, they would become positive ions, and they are called cations. And then nonmetals gain electrons. So they're gaining something negative, so they'll become negative ions, which are called anions. So as far as naming, because unless you see kind of representation of it, if you just hear the words, you have to know whether that it's become an ion. So as far as naming, the metals you would just use the regular name. And add ion. So for example, calcium 2+, if it has a charge up here as a superscript, that's telling you it's an ion. So this, instead of being called calcium, is now calcium ion. On the nonmetals, on the other hand, you have to do a little bit more work. So on the nonmetals, you're going to change the, yes, sir. Will you mind getting it for me? Change the ending to "ide." So for instance, if I just have an O, there's nothing around it, that's oxygen. So that's a neutral atom where the protons are equal to the electrons. But now if I have O with a -2, once it has that notated as a superscript, then it's telling me this is an ion. So instead of oxygen, I have to change the ending to "ide," so it would become oxide. And you can put ion, you don't have to. The fact that it has the name changed to that is telling you that it is an ion. All right, so let's look at how we would look at the subatomic particles if we had these. So let's start with calcium, a metal. So protons don't change. So that's still 20 for the atomic number. 40, still its mass number, but it forms a +2 or a 2+ ion. So to name that, that's a metal. So that would be simple. I just would keep the calcium name and I would have to add ion to it. All right, protons, once again, that's not what's changing. So I still have 20 protons. Neutrons, I still can get by doing my mass number minus my atomic number. So that's 20. But what is going to be different now is I have to figure out how many electrons. I don't have 20 because it's not neutral. It has a +2 charge. So remember, if it has a +2 charge, that means I've lost 2 electrons. So how many would I have now? 18, right? If you look at it, I have 20 things that are positive and 18 things that are negative. So that's why overall it has a +2 charge. And then the nonmetals go the other way. So we'll do the same thing if I had it's just I'll hand you my notes when I get through. I'm sorry. All right, let's do the same thing. This is sulfur. And it doesn't change its atomic number or its mass number. That's sulfur. But if I take the same thing and I put a -2 up there, now it's an ion. So now instead of sulfur, it's sulfide. And once again, you can put ion, you don't have to. We'll do the same thing. Protons, that hasn't changed. That's still 16. Neutrons, still going to do my mass number, my 32 minus 16. Now my electrons and protons are not equal. So since it's the -2, that means I have gained 2 electrons. So how many electrons do I have now? 18. And once again, if you think of that, I have 16 positive things. I have 18 negative. So that makes sense that I would have a -2 charge on that. All right. I think y'all have time to do a little bit of practice. And if you look at your practice, it's in your notes. I did it that way this time. It starts off with the easier one. And then it goes to in the back, then there are some with the ions for you to practice too with. Because you will have a quiz of this on Friday. And it'll look just like one of your practices. Oh, you good?